This continues the lectures on free fall. Now we start to take a look at example problems. When doing example problems, we will be using these two kinematics equations. We approach these equations a little bit differently, however, than we do when we were doing horizontal situations earlier in this unit. Typically in horizontal situations, just because it's easy to do so, we tend to think of the initial position x naught of the object as being equal to 0. Here we tend to think of the ground as the origin, however, when dealing with free fall examples, because it's an easy point of reference. So then therefore we approach the problems a little bit differently for that reason than we did earlier in the unit for horizontal situations. Okay, let's take a look at the first of our free fall examples. Let me read it to you. An object is dropped from rest from a height of 30 meters above the ground. When does the object hit the ground? And then what is the object's velocity the instant prior to striking the ground? When you see the terminology, by the way, written in the following manners, that is, the instant prior to striking the ground or the instant it hits the ground, it all means the same thing because an instant is literally a non-measurable amount of time. It's the last possible moment that an object is in free fall. After it hits the ground, it's no longer in free fall. We don't care what happens afterwards. We're only concerned with what happens during free fall. Okay, so let's begin to set up parts A and B of the problem in the following way. All right, so here's the ground. Once again, that's an easy point of reference, so we think of that as the origin. And then here's our object initially dropped from rest. So then therefore the initial velocity, Vy naught, is equal to 0 for that reason. The initial height above the ground that the object is dropped from is the initial position. So right here is the initial position vector, y naught, that's equal to 30 meters. And then we drop the object all the way down to the ground, the last possible moment that the object is in free fall. Its final position y is equal to 0. It has an unknown final velocity v sub y, and this takes place in an unknown amount of time t. The whole time, of course, the acceleration is downwards at 9.8 meters per second squared. So once again, I'm always using the same method of solving a physics problem, drawing a simple diagram, writing down the knowns and unknowns, and so on. And now we begin our mathematical analysis. When I begin my mathematical analysis of the problem, let's actually begin by taking a look at the position equation first. In the position equation, two things here are equal to 0, the final position and the initial velocity. So then therefore the position equation simplifies to become the following. And now if you look at the expression carefully, you'll notice that the only unknown here is the time t, which we can now solve for. So to do so, move the 1/2 gt squared here to the other side, like so. Cross multiply by the 2 and the g to the other side, and then take the square root. In doing so, you end up with the following expression, like so. And now I can go ahead and plug in my numbers. When I plug in my numbers, I plug in just 9.8 meters per second squared for g. I don't plug in a negative number, and the reason for that is because the negative sign is already taken care of in the equations. We just plug in the magnitude. All right, so let's go ahead and find that result. So square root of 2 times 30 and then divided by 9.8, and that works out to be 2.47 seconds. Okay, now that I have that time, let's now switch to the velocity equation. In the velocity equation, the initial velocity is equal to 0. So the equation becomes the following. And now let's just go ahead and plug in our numbers. 2.47 seconds multiplied by g, and I end up here with negative 24.2 meters per second. The negative sign here simply means that the final velocity vector is downwards in the negative direction, and the final speed of the object would be the magnitude of that value. So this is the simplest example. What happens if you just simply drop an object from rest? Okay, let's move on to the next example. The next example is sometimes what I refer to as the basic free fall problem. What we're going to do is take an object, initially throw it upwards like so, and then calculate out a bunch of different quantities. Let me go ahead and put the problem for us here onto my screen. Okay, go ahead and copy down that problem into your notes while I erase the board. Okay, and then here's what we're given. An object is launched vertically upwards from the ground with an initial speed of 50 meters per second. In part A of the problem, what is the maximum height reached by the object? Okay, so once again, here's the ground. We think of that as the origin, but in this case, we're launching from the ground upwards like so. So the initial velocity upwards is given to us as 50 meters per second. The initial position y naught is equal to 0. And then in part A, when we reach the maximum height like so, we do so for an instant, and at that instant, the velocity v sub y is equal to 0. So it doesn't explicitly say that the final velocity is equal to 0, but the instant that the object reaches its maximum height, at that instant, the velocity is at 0. Okay, and then the unknowns are as follows. Right here is the final position y, that's the maximum height reached, nor do we know the time t. Now, because we are given that the final velocity here is equal to 0 at this instant when the object reaches its maximum height, let's begin our mathematical analysis of the problem by using the velocity equation. In the velocity equation, on the left-hand side, the v sub y is equal to 0. Like so. And now we just solve for the time t. So to solve for t, move the gt to the other side, and then divide by g to now get the time t by itself. That is like so. And now I'll just go ahead and plug in my values, and this is the time necessary for the object to rise to its maximum height. So then therefore I have 50, and then divided by 9.8, and this comes out to be 5.1 seconds. Okay, now that I have that time, let's just now switch to the position equation here, plug in all the values with this known time, and then calculate the maximum height. So in order to do so, I'm just going to plug everything into the expression. There's no algebraic steps to perform here. So I have 0 and then plus 50 times 5.1, and then minus 1/2 times 9.8 times 5.1 squared. Don't forget the minus sign here. And when I calculate this out, this ends up being about 127.55 meters. Like so, that's the maximum height reached. Okay, next let's take a look at part B. I have to move it on my file. Okay, in part B it says, when and with what velocity does the object hit the ground? What I'm going to do, however, here for part B of this particular problem is just this one time I'm going to solve it 2 different ways. What you will begin to discover is that there are multiple ways to solve various physics problems. Sometimes one method may be a little bit easier than the other. You will gain experience the more problems that you perform. So just to illustrate that, just this one time, I'm going to do part B of the problem 2 different ways. Okay, so let me call this first of all, for part B, let me refer to this as method 1. Okay, what I'm going to do for method 1 is I'm going to drop the object from rest at its height of 127.55 meters, and then just calculate what happens when it returns to the ground. Okay, so here's the object now initially at rest, like so, with an initial position y naught of 127.55 meters, and then we drop it all the way down to the ground with a final position y equal to 0. This takes place in an unknown amount of time t, and then right here is the unknown final velocity v sub y. Before I calculate out these values, can you tell me ahead of time what the time necessary to fall down to the ground is going to be? Can you tell me what the final velocity v sub y is? Think in terms of symmetry. Because ultimately, when describing the position as a function of time for an object that is being thrown upwards, it's a parabola. And what we're doing here in parts A and B of the problem is just looking at the different sides, on opposite sides of the vertex of that parabola. Let me illustrate here as I begin to mathematically solve the problem. Okay, we're basically taking an object here and dropping it from rest. So let's begin right here with the position equation. In the position equation, 2 things are equal to 0. The final position and the initial velocity. So let's go ahead and plug the zeros into the expression like so. And I get this equation here, much like we saw earlier in the opening example. And now the only unknown there is the time t, which I can now solve for. So move the 1/2 gt squared to the other side. And then cross multiply the 2 and the g over to the other side. Take the square root now to solve for the time t. So after you do those mathematical steps, you end up with this expression here, and now I'll go ahead and plug in my numbers. Notice, by the way, that this equation here is different than this equation here, which I derived earlier. And the reason for that, in part A of the problem, my opening step involved the velocity equation. This instead, however, involves the position equation. Let me go ahead, however, and plug in at this point. So I have here now the square root of 2 times 127.55, and then divide by 9.8. And lo and behold, this is also equal to 5.1 seconds. 5.1 seconds to go up and 5.1 seconds to go down. Once again, we're seeing symmetry here about the vertex of a parabola. By the way, at the end of the example, I'll go ahead and graph out the problem so we can see the symmetry that I'm alluding to. Okay, now, continuing this method, let's go ahead and solve now for v sub y, the final velocity. In order to do so, we'll use the final velocity equation, where once again, we're dropping the object here from rest. So the velocity equation then therefore simplifies to become the following, and now let's plug in. Watch what happens when I do. So 5.1 seconds multiplied by g, and this ends up being negative 50 meters per second. So the object leaves my hand at 50 meters per second, and it returns to my hand at 50 meters per second as well. Once again, we're seeing symmetry here about the vertex of a parabola. Now that's one way to do part B. However, I can do part B another way if I wish. Once again, just this one time, I'll solve part B here twice. Okay, so let's say I approach part B in the following way. Okay, once again, here's the ground. But now in this case, we'll begin at the ground. The initial position y naught is equal to 0, and we throw the object upwards with an initial velocity of 50 meters per second. But now what I'll do is I'll say the object returns to the ground, so its final position y is equal to 0. It will do so with an unknown final velocity v sub y, and this takes place in an unknown amount of time t. So let me set up part B of the problem like this. Now, because both the initial and final positions are equal to 0, let me begin my mathematical analysis of the problem now by using the position equation. That is this expression here, where both y and y naught are 0. Like so. And now if you look at the expression carefully, you'll notice that there's only one unknown, and that's the time t. But it is a quadratic. So then therefore there are two solutions. One of the solutions, however, for the time t is 0. Notice that 0 is equal to 0 minus 0. And that makes sense, and the reason why is because at times t is equal to 0, the initial position of the object is 0. However, we don't care about that time, we want to solve for the other time. Now, because this is 0 on the left-hand side of this expression, I can now go ahead and safely cancel out a t from each term here on the right-hand side. And then when I do, the only time that remains is this value here, which I can now solve for. So let's move the 1/2 gt to the other side, like so. And then just cross-multiply the 2 and the g to the other side to obtain the following. This expression here. Notice that this expression here is twice as much as the expression here to go upwards in part A up on the top board. So then therefore the answer is the total time here of 10.2 seconds. And then lastly, for this second method here of doing part B, let's just now go ahead and find the final velocity. To do so, we'll just plug everything into the expression here. There's no algebraic manipulation to perform. It's 50 minus 9.8 times 10.2 seconds. So then therefore, 50 minus 9.8 times 10.2, and sure enough, the answer for v sub y is negative 50 meters per second. So either method for doing part B is perfectly fine. Once again, with experience, you'll find perhaps that one method is a little bit easier than the other. Okay, lastly is part C. In part C of the problem, we're looking at a specific point on the parabola that describes the position as a function of time. It says when and with what velocity is the object at a height of 10 meters above the ground. Okay, so now let me approach part C in the following way. Once again, here's the ground. We're going to launch upwards from the ground. So the initial position y naught is equal to 0. And then here's the initial velocity, once again, of 50 meters per second. And then we're going to end up here at a height of 10 meters above the ground. So that's going to be our final position y for this portion of the problem. How many times is the object going to be at that height? Twice. Once on the way up with a velocity v sub y, and once on the way down with another velocity v sub y, and the time t here is unknown. Once again, we'll see symmetry in the problem as we proceed. Okay, now mathematically we proceed here for part C in the following way. Because we are given the final value of the position y as 10 meters, let's begin with the position equation. In the position equation, the initial position y naught is equal to 0. So that equation becomes the following. And now once again, the only unknown here is the time t. How am I going to solve for the time t? I'm going to get, once again, two values because this is, in fact, a quadratic. In part B, earlier, the left-hand side of the expression was equal to 0, but not so here in this case in part C. In this case, it's a value of 10 meters. So then, therefore, what I have to do is I have to use quadratic formula to solve for those two times. Who would have thought that quadratic formula is present here in perhaps one of the simplest of all physical phenomena, an object in free fall? But it is. In order to see how the quadratic formula is going to work here, what I'm going to do is I'm going to take these two terms here and move them to the left-hand side of the equals sign. That will then give me the following. Like so. And now my coefficients A, B, and C of the quadratic formula are as follows. The coefficient A is the 1/2 g that's in front of the t squared. The coefficient b, including the negative sign, is negative vy naught in front of the time t, and then the constant here of 10 meters, that right there is the value of c in the quadratic formula. Okay, now let's go ahead and solve for our unknown t using the quadratic formula. That will then be as follows. First of all, in the numerator of the expression, you have negative b. So the negative of negative vy naught is positive vy naught. And then plus or minus two answers, the square root of b squared minus 4 times a times c. And then all over 2 times a, like so. So if necessary, refresh yourself on the basic form of the quadratic formula using the coefficients a, b, and c. I'm writing them here specifically for this case. Okay, let's go ahead and simplify the expression. It does simplify a little bit. First of all, in the denominator, you'll notice that the 2's cancel out here and here. And then underneath the radical sign, this negative sign here is going to square. So I'm going to just go ahead and get rid of it. And at this point, I'm going to go ahead and now start to plug in my numbers. Let me show you what the numbers are as I proceed. Okay, so first of all, we have right here 50, and then plus or minus the following. I'm going to go ahead and do the radical sign here using my calculator. So I have here 50 squared, so that's 2,500, and then minus then, there's a 2, by the way, that cancels here and here. Let me go ahead and do that as well. So minus 2 times 9.8 times then 10 meters, excuse me. That's the height that we're looking at here, 10 meters. So 2 times 9.8 times 10. There we go. Take the square root of that, and that comes out to be 48. And then divide by g, which is 9.8 meters per second squared. Okay, now watch what happens when I use the minus sign here in the numerator. This will be the lesser amount of time. This is the time on the way up. So 50 minus 48 is 2, and then divided by 9.8, that ends up being 0.2 seconds. And then the second time occurs when I use the positive sign here in the numerator. That'll be the time on the way down. 50 plus 48, and then divided by 9.8, that's actually a total of 10 seconds. So once on the way up and once on the way down. And now lastly, using these two times, let's go ahead and find the velocity v sub y. One will be a positive value, one will be a negative value, and as we'll see, they'll have the same magnitude. All right, so to find then those two values of velocity, all that I have to do is use the velocity equation and plug into the velocity equation the two values of the time. So there's no algebraic manipulation to perform here. I can just go ahead and calculate these values. So here's then what I obtained. First of all, on the way up, we're going to have 50 minus 9.8 times 0.2. So 50 minus 9.8 times 0.2. And this works out to be positive 48 meters per second. And then watch what happens on the way down. On the way down, we'll use the time of 10 seconds. So 50 minus 9.8 times 10, this comes out to be negative 48 meters per second, once on the way up and once on the way down. Notice that that number that we just calculated is the same thing as this, the radical sign from the quadratic formula from earlier. This is not a coincidence. The reason for that is because if you go back into your notes and you look at that radical sign carefully, you'll notice that it's the third kinematics equation for the velocity v sub y. It will always work out this way mathematically. It's just how the algebra is performed here with these examples. Okay, obviously over the course of this problem, I've been hinting at symmetry as I go. So the last thing that I want to do here is just graph out the velocity and the position as a function of time for this problem to show all the symmetry that occurs. Okay, so first of all, the velocity as a function of time. Recall for an object that is thrown upwards that the velocity as a function of time equation is linear, and the graph of that looks like this. Like so, with a slope, of course, of minus g. Okay, now right here is the initial velocity upwards of 50 meters per second. Right down here, at the end of the problem, is the velocity of negative 50 meters per second when the object returns to its original height. This right here would be the total time, then, therefore, of 10.2 seconds. We reach the maximum height here with a velocity of 0 at this instant at 5.1 seconds. And then, in part C of the problem, we had our other two times and our other two values of velocity. Right here, say at 0.2 seconds, that's when the velocity at this instant, right here, was at positive 48 meters per second. And then over here on the other side, right over here is 10 seconds like so. Right there at that instant, the velocity downwards was negative 48 meters per second like so for part C of the problem. So once again, we're looking at symmetry here on this graph on either side here of our point where the velocity was 0 when the object reached its maximum height. Okay, here is then the parabola associated with that when we graph out position as a function of time. So time in seconds, position in terms of meters, and then right here is our parabola, like so. So right here, of course, is times t is equal to 0. Right here is the maximum height of 127.55 meters. Right here is the time to reach the maximum height of 5.1 seconds. Right here was the total time of 10.2 seconds, like so. That's basically parts A and B. And then for part C, right here is 0.2 seconds, like so. Where right here at this instant, the height was 10 meters. And then on the other side of the vertex over here, this is also the height of 10 meters. This was the other time, like so, of 10 seconds. Notice, by the way, some other symmetry that occurs here. This time interval of 0.2 seconds here is the same thing as this time interval here of 0.2 seconds as well. Okay, let me go ahead and pause here for the video. Let me pause here for this portion of the lecture.